Welcome back, y'all, to the work that we're doing to prove that the matrix arising from our linear algebraic nodal analysis algorithm, AR transpose GAR, is non-singular. Recall this was a four-step process. In the first extension video to step 11, we proved that that matrix was non-singular if and only if the matrix A sub R had rank n, or the columns of that matrix were linearly independent. In part 2 of our extension videos, we showed that a matrix A, which models a connected graph, so this is an incidence matrix modeling a connected graph with F nodes. There's a theorem in graph theory that says that that matrix has rank F minus 1. So the number of columns in that incidence matrix, the number of nodes in the graph, the number of linearly independent columns is 1 minus that number of nodes. In this third part of our extension to step 11, we're going to prove that theorem rigorously, and then we're going to use that in part 4 and argue that A sub R actually comes from deleting one column of an incidence matrix corresponding to the deactivated resistor circuit digraph model. Thus, A sub R has full column rank, and that matrix is non-singular. With that in mind, let's prove this theorem for the rank of incidence matrices for connected graphs. Specifically, we saw this in the last video. If we have an incidence matrix A with M sub R rows and F columns that models a connected graph, then the rank of that matrix is F minus 1. Another way to say that is the number of linearly independent columns of A is 1 minus the total number of columns of A. We're going to actually develop the proof in general, so this will hold for any incidence matrix, but we're going to filter that result through the specific matrix that we generated for the deactivated resistor circuit digraph model. With that in mind, let's begin our proof. Suppose we have a connected graph with M sub R edges and F nodes, and we create the corresponding incidence matrix for that connected graph called A. Let's go ahead and create the column partition of our incidence matrix. So we'll say that A has F columns. Here's column 1, column 2, all the way down to column F using colon notation. We note that in each row of A, because it is an incidence matrix, there are only two non-zero entries. One of them has value positive 1, the other one has value negative 1. The positive value corresponds to the node from which that particular edge comes out. The negative value corresponds to the node from which that particular edge runs in. All other entries in that row are 0. The moment that we know that each row has exactly two non-zero entries, one of which is equal to 1 and the other one is equal to negative 1, we know that there is a non-zero vector x1 that sends the matrix A to 0 via right multiplication. Specifically, if I were to multiply A on the right by the vector of all ones, so put F ones, 1, 1, 1, all the way down to 1, count F of those, create a vector x1, here's a claim. If I multiply A times x1, I'm for sure going to get 0. Indeed, that's true for our specific incidence matrix associated with our circuit example. When I multiply by 1, 1, 1, 1, 1, a vector with 5 ones lined up, that's equivalent to adding all the columns together. But in each row, I take a scalar multiple of 1 times the entry in that row, and I do a sum. Each row sum is going to be 0, and that's that statement. This implies, though, that we can find a non-zero vector that when multiplied by A gets sent to 0, which means that the columns of A cannot be linearly independent, which means the number of pivots of columns of A cannot be equal to the number of columns. So we know for sure that the rank of A is bounded above by at least 1 minus the total number of columns. Remember that the rank of A counts the number of linearly independent columns. We've just seen that there is at least one linearly dependent column, or at least one way to send the matrix to 0 with non-zero scalar coefficients. The format of this proof is actually going to be show the reverse is true as well. Not only do we show that the upper bound for the rank of A is f minus 1, but we're going to show that the rank of A must be at least f minus 1 as well. In other words, we're going to say that the rank of A is less than or equal to f minus 1 and greater than or equal to f minus 1, which means it's exactly equal to f minus 1, and that's where we're going to go in the next part of this proof. Suppose, hoping for contradiction, that the rank of our matrix is strictly less than f minus 1. If that was true, if we know that the total number of linearly independent columns of our matrix was less than 1 minus the total number of columns, then I should be able to get a second non-zero vector that is linearly independent from my first non-zero vector. Remember, our first non-zero vector that sends A to 0 is the vector of f1s. We can now find, if this assumption was true, we could find a second value not all equal to 0 such that A times x2 is equal to 0. Let's make some specific observations about our vector x2, which is non-zero. And we're going to say that not all entries of x2 are 0. The point of this is that the rank is less than f minus 1. So we should have a non-zero vector that sends the columns of A to 0. In other words, not all entries of that can be 0. Similarly, not all entries of this thing are equal to 1 or even scalar multiples of 1, because if that was the case, x2 would be linearly dependent on x1. As a friendly reminder, the reason that we can make this conclusion refers back to a theorem that we studied when we studied solution sets for general linear systems problems. Remember that we said that the number of columns of our matrix A is equal to the number of pivot columns in that matrix plus the number of non-pivot columns in that matrix. In other words, every column is either a pivot column or a non-pivot column. By definition, we said that the number of pivot columns was equal to the rank of A, or the number of linearly independent columns of A. And then we said that the number of non-pivot columns was equal to the number of linearly independent solutions to the homogeneous linear system problem involving the matrix A. So if I looked at this type of solutions to AX equals 0, if I want to know the number of linearly independent solutions, I can say that, well, that's equal to the number of columns minus the rank. But in our assumption that we're looking to force a contradiction from, we said that the rank of A was less than f minus 1, which means that there are at least 2 linearly independent solutions to the homogeneous linear system problem. X2 is the second version of that. If it is linearly independent, it cannot be a linear combination of x1. Thus, we can conclude that not all entries of x2 are equal to 1, or that x2 is not in the span of x1. The third observation that we're going to make is that we can restrict our focus for each entry of x2 to be either 0 or 1. In other words, if I look at the f entries of my vector x2, I'm going to choose the values of that to be either 0 or 1 for every entry possible. This third observation is a bit subtle, but let's take a look at why this is true. Remember that the matrix A is an incidence matrix for a digraph model of a connected graph, which means that in every single row, there are exactly 2 non-zero entries, one of which is positive 1, the other which is negative 1. All other entries in that row are 0. We are searching for a vector x2 such that when I multiply A times x2, I get 0. Well, if that's true on the matrix vector equation side, it's definitely true on the scalar side. Or if I look at the individual rows of the matrix A, when I take the jth row of A and I multiply by x2, I should get the scalar 0 for every single possible row. Let's take a look at what that actually means in our specific example. When I'm looking at my incidence matrix A, I can multiply all the individual entries of that by the coefficients of my vector x2 that I'm searching for, and I get 0, and that's true for each individual entry. Let's go ahead and focus in on row 1. Row 1 of my matrix A was 1, 0, 0, 0, negative 1, and then I'm searching for at least one non-zero scalar in the vector x2 such that This row times that vector is the 0 scalar. But when I look at that, one of those entries is going to be pulled off with a positive scalar, 1, and the other one's going to be pulled off with a negative 1 scalar. And when I add those two together, I get 0, which says that at least two of those entries have to be identical. We could do a similar analysis for row 4. Row 4 of our matrix is 0, negative 1, 0, 0, 1. When I multiply that row 4 by my unknown and desired vector x2, that immediately claims that the second entry is going to be identical to the fifth entry, but we knew from the first row 1 that the first entry was going to be identical to the fifth entry, so all of those values are identical. We could actually choose any non-zero number. We could choose 5, 7, 10, etc. But since they're all scalar multiples that are identical to each other, why don't we just focus on the number 1? Because literally we're just trying to figure out how do we combine those to get 0. Of course, we're not claiming that the specific example that we're analyzing proves the general statement. What I am claiming, though, is that that pattern that we're noticing in the example incidence matrix actually holds for any incidence matrix connected to a directed graph. Thus, when we're looking at the entries of our non-zero vector x that send that matrix to 0, we're going to claim that we can restrict our focus to either zeros or ones. Some of them have to be zeros, some of them have to be ones. The next observation I want to make is that there must be at least two non-zero entries of x2. In other words, if x2 only had a single non-zero entry such that a times x2 was 0, that would imply that in one of those columns there were all 0 entries, and a column with all 0 entries corresponds with an isolated node. But we've said originally that the graph was connected. If the graph is connected, we should be able to get from any one node to any other node. In other words, no isolated nodes exist. Thus, it must be the case that there are at least two non-zero entries of x2. Moreover, because we know that at least one of the entries of x2 should be 0, that immediately implies that at least two of the entries of x2 should be 0. Otherwise, we would have an isolated node. If you had only one entry of x2 to be 0 and all other ones were non-zero, that would mean you had a cluster of nodes. In fact, f minus 1 nodes were connected together, and one of them wasn't connected and would be sent. So these two are kind of the dual of each other. There should be at least two non-zero and at least two 0 entries of x2. But these observations lead to our contradiction. Specifically, we're saying that we should be able to find a non-zero value of x2 such that a times x2 is 0. At least two entries of x2 are non-zero. At least two entries of x2 are 0. And all entries of x2 are either 1 or 0. I'm going to make the claim that within this structure, we should be able to reorder the edges and nodes so that we can yield a block diagonal form of A given by A equal to A1, so some set of nodes that are all connected together by edges, 0, 0, A2, some other set of nodes that are connected by edges, where no edges go from the first set of nodes to the second set of nodes. That is implicit in these observations about that incidence matrix. And specifically, that means that the matrix A1 encodes a component of our graph that is connected within itself but has no connections to the second set of nodes, and vice versa. But the fact that we could produce that block diagonal partition of the matrix A simply by reordering the edges and reordering the nodes means there are two subgraphs that are disjoint collections of nodes and edges, but that implies that our graph is disconnected. That's a contradiction. We started with the assumption that the graph was connected, and then we imposed an additional assumption that the rank of the incidence matrix for that connected graph was strictly less than f minus 1. That led to a contradiction that said the graph was disconnected. This immediately means that no such non-zero x2 exists, or the only non-zero x that sends A to 0 is the x with all ones in the entries. that means that the rank of that matrix cannot be less than F minus 1, which means the rank of the matrix is greater than or equal to F minus 1. But now we have the rank of the matrix is less than or equal to F minus 1 and greater than or equal to F minus 1, which means the rank of that matrix is exactly F minus 1. That was the theorem that we were going to prove. With that, we finished our formal proof of this theorem, and you could go ahead and check that for this specific matrix. If you were to add any column to each other such that not all scalars on those columns were equal to 1, so at least one of the columns has scalar 0, note that you'll never get to 0. The only way to combine these columns and get to 0 is if you add all the columns together. You can go ahead and check that for yourself. We've just made a much more general proof of that statement. In the next video, we're going to leverage this theorem to wrap up our proof that the incidence matrix from the linear algebraic nodal analysis algorithm is always non-singular. I'll see you in the next video.